So again, you guys are going to kind of split your page kind of two graphs. So the very first graph that I'm going to be doing is going to be a parabola. So this is a parabola. And if you want to write this below where you guys underneath where it's lined, I would write this maybe where it's lined on yours. Does that make sense? So that you can use the graph for the graph. So don't write the name and the equations where your graph paper is. Write the name and equations down here on the line part. Does that make sense? Okay. And so our basic equation is going to be y equal x squared. And that's kind of, I'm going to put it right next to it. That's kind of our parent, y equal x squared. Our general equation is y equal a times the quantity x minus h squared plus k. Okay, again, for those of us doing our notes in our comp book, do it on the lined part. All the writing, we'll do the graph on the graph part. Our vertex is going to be h comma k. And then we talked about the movement the other day, but let's have it here officially. So when we're doing this, remember our A, if it is greater than 0, which basically means positive, it's going to open up. If our A is negative, which means less than 0, it's going to open down. Now, also in terms of our A, if our A in absolute value is greater than 1, meaning it's like a 2 or negative 2 even, something in absolute value greater than 1, it is going to be narrower. Okay. We call that vertically stretched here. I'm just going to write narrower. And if our A in absolute value is between 0 and 1, it's going to be wider. And let's see, let's see if I can change that color. Okay. Then when we're talking about the x minus h and x plus 8 part of this, so if it's an x minus a number, that means we're going to go right h. It's whatever makes that parenthesis 0. And here I'll put the square there too. That x minus h squared part of it, okay? And if we have the quantity x plus h squared, that means since a negative is going to make that 0, we're going to go left h. And then the last bit of this is our k. And so we have a plus k, which means we're going to go up k, or we have a minus k, which means we're going to go down k. Now, when we're going to graph the parent equation, and for this, I think we're going to, let's do our parent equation, and next to it, let's do one that's moved. So we're going to just have parabola right here on this page, okay, for us. Anyone still copying that down before I move my screen? So I'm going to move mine down, but you guys are going to put this on the graph paper, okay, on your graph paper. So what I'm going to do is I'm going to graph the plain old y equal x squared. And when we're graphing this, we will only in this situation have positive values. So you can draw your x and y axes all the way down where your x-axis is at the bottom of your graph, okay? And when I'm graphing y equal x squared, sorry, I'm thinking about squaring my values. So the very first thing I'm going to do is if I was to put 0 in here, 0 squared is 0. So I have a point at 0, 0. If I was to put 1 in here, 1 squared is 1. So if I went over 1 for 1 squared, I go up 1. It's going to be the same on the other side. I'm just going to kind of zoom in a little bit more here so we can see the grid a little better. When I go out 1, 2, 2 squared is 4. So I'm going to go up 1, 2, 3, 4. And I'm going to go out 3, 1, 2, 3. And 3 squared is going to be 9. So I'm going to go up 9. So that's my 4, 5, 6, 7, 8. Need to shrink it down a little bit. Okay. So that's 4, 5, 6, 7, 8, 9. So again, I went 1, 1, 2, 4, 3, 9. And then I am going to connect these points with a curve. And that is my parabola. Something I'm going to state for this is I'm going to state the domain and the range. Okay. My domain for this particular graph is going to be all real numbers, basically. So the way I'm going to write that is I'm going to go negative infinity with an open bracket to positive infinity, negative infinity to positive infinity. And my range is going to be close bracket because it actually touches at 0. So when I say close bracket, it's going to be square bracket to infinity. So your domain are your x's, your y's are your range. Okay. Again, what we're going to be writing, put on the line paper part of your composition book. Okay. And so this next one is going to be exponential function. Now, kind of our parent one, usually we have as y equal 2 to the power x. Okay, y equal 2 to the power x. And for this, we have an asymptote. Our asymptote is a horizontal asymptote. It is the x-axis, which is y equals 0. That is our asymptote. Our general equation is y equal a times b to the power x, which is what we did in integrated 1. Now we're going to have a minus h with that exponent. That's still going to be our left-right movement. And then we're going to have a plus k. And so for this one, our asymptote is going to be that plus k. So y equal k. That is going to be our asymptote. Now, in this case, when we're talking about our a, it's still what we consider a stretch. But this a is going to be our y-intercept. That's what it's going to be. It's going to be our y-intercept. Okay. And maybe I shouldn't say y-intercept, because let me say it this way, because we're going to be shifting this. It's going to be our start. Okay, it's going to be our start. And I'm putting it in quotes. Our b is going to be what we call our multiplier. It's what we're multiplying by. Now, when I'm talking about that x minus h, or that x plus h part of this, just like a parabola, this is going to move right or move left. Okay, that's what it's going to do. The plus k part of it and the minus k, this is where your asymptote's going to be, and it's going to move graph. It's going to move up k or down k. So for this one, when we are graphing this, I always personally start with my asymptote, okay? And I'm going to have us graphed as y equal to the power x to start with. Raise your hand if you're still copying. Okay. Okay. So, for this, if I am graphing, as an example, y equal 2 to the power x, okay? For this, also, we will have everything above the x-axis. So we can draw our graph so that we are just having everything above. Now, for this, we're going to have an asymptote. And our asymptote is a line that the graph gets closer and closer to. And the asymptote is actually going to be right here on the x-axis. And the equation of that is y equals 0. So we have a dashed line, or sometimes I'll draw it with a highlighter, like the highlighted line, so that you can kind of see through it. Maybe I'll do that. So let me just get a highlighter. So again, it's really a dashed line, but I'm going to do it like this. Now, in this case, that is a 2. My multiplier is 2. So if we're trying to identify the pieces here, my A is actually a 1. I don't have an A in front. My B, my multiplier is a 2. This is my multiplier. So the way I generally teach this to my integrated ones is we're going to start at our start, which is going to be the y-axis. And what we're going to do when we're graphing this is our first point is going to be RA. RA is 1. So I'm going to be right here at 0, 1. Okay, so it's my y-intercept unless it gets shifted. That's why I erased it and didn't say y-intercept. Now, what we're doing is every time we are timesing by 2. So if this, and I'm just going to zoom in a little bit, if I am literally here at 1, my next height, I'm going to double 1, and I'm going to be 2 above my asymptote. And then I'm going to come over here and I'm going to double 2. Now I'm going to be at 4. And then I'm going to double 4. So I'm going to be at 8. So let me just kind of write these values so you know this was at a height of 1, this was at a height of 2, this was at a height of 4, this is at a height of 8. I'm timesing by 2, timesing by 2. The next one's going to be 16. Okay. And then what's going to happen is when I'm drawing this, it's going to be coming and getting closer and closer and closer to the x-axis like that. Okay. So once we get that, again, we're going to leave the next part of that blank. We're going to go to the next page and we're going to add a different graph in. Okay. Right now, I'm just trying to get the parent graphs out to you guys, the ones we didn't get to on Friday. Anyone still copying this? Raise your hand if you are. Okay. Okay, so the next one I'm going to do is a reciprocal function. Okay, so again, this you're going to be writing on your paper, the line paper part. This is called a reciprocal function. And our basic equation for this is y equal 1 over x. That's kind of our basic equation. Now, we have a general equation, and our general equation is going to be the following. Y equal, the ones we're going to be seeing are going to be the number 1, but there's really could be an A on top instead of a 1. Right now, our A is 1. And instead of this being an X, it could be an X minus H, which is again going to move it left or right. And then a plus K. Now, what's going to happen for these are going to have 2 asymptotes. So the original one, y equal 1 over x, has 2 asymptotes. Okay. The asymptotes are the following. It's going to be the x-axis and the y-axis. I'm going to have x equals 0, and I'm going to have y equals 0. I have 2 asymptotes. For this general equation, I'm also going to have 2 asymptotes. It is going to be whatever makes the denominator 0. So since it's an x minus h, what makes that 0 is x equal h. And then the plus k, that's going to move your graph up. So you're going to have one at y equal k. Okay. Now I'm going to leave the rest of that part blank right now, and I want us just to sketch this. Okay, so we're going to do the graph. I'll leave some space on mine to add something in later, but I want us to get like the graphs in. So for this, let's say we do y equal 1 over x. Okay. This one, you're going to need your x and y axis centered. Okay. So this is going to be on your graph paper. Anyone still copying the words? Okay. So I'm going to have an x and y axis that are centered this time. Now, if I was to rewrite this equation, we actually saw this in integrated one when you guys did the hot tub problem. You ended up with this reciprocal function graph is what you guys ended up with. If I multiply both sides by x, this is really xy equal 1. So really, I want things that multiply to 1. That's really what I want. Things that multiply to 1. 1 and 1, 2 1/2, 3 1/3, 4 1/4. That's really what we want. Now, for this, I am going to have two asymptotes. I am going to have a horizontal one on the x-axis, which is going to be y equals 0. I am going to have a second one that is going to be on the y-axis, which is going to be x equals 0, x equals 0. Those are going to be our asymptotes. And what's going to happen is, for this, I'm going to ask for one accurate point. Okay, the rest of them are going to be approximations because they're going to be basically a lot of fractions or decimals. So if I went over to 1, and I'm thinking about this, if my x is 1, what can I times with 1 to get 1? So my point's going to be 1, 1. That's the point I want you to accurately give me. Okay, 1, 1. Well, what else multiplies to 1? Well, a -1, -1. So I'm also going to have a point at -1, -1. Those are the two accurate points I want. The other points are basically, you're just going to kind of draw a curve. And what's going to happen is it's going to be getting closer and closer to that asymptote and closer to that asymptote. We have two branches. That's what we get. That's going to be our graph. Okay. Now, I added domain and range for the first one. We'll come back and add domain and ranges on these other ones, okay? Something we do need to know, but I want us to get the graphs out. Okay. So the only points I want us to be accurate with, that one and that one. The other ones are just curving, okay? That's it. And why are those ones? Because 1 times 1 is 1, and -1 times -1 is 1. That is why. Anyone still copying this? Okay. Next page. And we'll add on ones that are moved as examples for us, but today we're going to get the parents out there. Okay. We aren't going to use as many pages every day. Okay. These are ones that are your reference ones. Does that make sense? And if I need to get another composition book, I'll get you another composition book. Okay. But, usually I do have one per page on this anyways, even if it was a regular composition book. Okay. Next one. I'm going to do square root graph. Square root. And our basic square root graph is y equal the square root of x. I'll call it a vertex, but it's really like our starting point at 0, 0, but it's kind of like our vertex. General equation. y equal a times the absolute value of x minus h plus k. That is our general equation. Okay. And our vertex for this, or our starting point, is going to be h comma k. And for you guys, again, we'll leave the rest of that space blank right now. And let's just get the parent equation in. So if I have the square root of x, can I take the square root of a negative number? I can, but I'm going to get imaginary numbers, right? I'm going to get imaginary numbers. So we're only going to be taking the square roots of basically 0 or positive numbers. That's what we're going to take the square root of. So if I'm doing this graph, and for this graph, again, this graph is only going to be above the x-axis. Okay, so when you're drawing your grid, you can make it above the x-axis. And to be honest, we could actually even kind of shift it this direction if you want. Because I'm not going to take the square root of a negative. So the first value I'm going to do is 0. What is the square root of 0? 0. So I'm going to have a point at 0, 0. Okay. What is the square root of 1? So I'm going to go to 1 comma 1. So I'm kind of making a table, but I'm just kind of doing it in my head. Is the square root of 2 nice? It's like 1.414. No, I don't want to graph that. Is the square root of 3 nice? Is the square root of 4 nice? Okay, so I'm going to go to 4. 1, 2, 3, 4. What's the square root of 4? 2. There you go. Just graph that. Just graph the nice ones. What's the next nice square? Or square root, I should say. 9. Square root of 9 is the square root of 9 is 3. So I'm going to go 1. I'm going to go to 9. So that's 4, 5, 6, 7, 8, 9. And the square root of 9 is 3. Okay. And then I can do more. I could take the square root of 16 is 4 and so forth. But this is going to be my graph. Really what it is if I took a parabola and turned it on its side, it's half of a parabola. That's really what it is. Okay. So in terms of points, I plotted again 0, 0. This was 1, 1. This is 2, 4. This is 2, 4, 4, 2. I apologize. And this one is 9, 3, because I took the square root of 9 and I got a 3. I took the square root of 4, which is a 2. My next one would be at 16. That would be 4. And that is our square root. Okay. Now, next one on next page, cubic graph. Cubic graph. Okay. Anyone still copying this before I move it? Okay. So cubic. A cubic graph is y equal x cubed. Okay. And this has what we call an inflection point at 0, 0. My general equation is going to look like a parabola equation. Y equal a times the quantity x minus h. Instead of it being squared, it's cubed, plus k. And again, my inflection point is going to be whatever makes the x minus h 0, which is h, and then the plus k. That is going to be our inflection point. And inflection point is going to be like our locator point, and I'll explain what it is here in a second. It's going to be kind of like our center of our graph. So I'm going to graph y equal x cubed. Again, you guys can put this on the graph part. So if I graph y equal x cubed, for this one, I need to have the xy axis centered. Okay. Okay, I need to have it centered. I'm gonna zoom out for a second so I can draw mine in. Okay. So I'm cubing numbers. Okay, I'm just cubing. What's 0 cubed? 0. What's 1 cubed? 1. What's 2 cubed? So when I go to 2, I'm going to go up to 8 because 2 cubed is 8. So 1, 2, 3, 4, 5, 6, 7, 8. So again, this one is 2, 8. This one is 1, 1. This was 0, 0. Now, the next one would be 3, 27 because 3 cubed is 27. 4, 64 because 4 cubed is 64. They're not going to fit on my graph. Now, what is negative 1 cubed? What's a negative times a negative times a negative? So it's going to be a negative 1. So unlike a parabola where a negative squared and a positive squared are the same, a negative cubed is a negative. So when I go to -2 and I cube -2, I'm going to get -8. 1, 2, 3, 4, 5, 6, 7, 8. So this point here was -1, -1. This is -2, -8. Okay. And when I say inflection point, notice that this is almost like an open up, half of an open up parabola right there. See how it's kind of opening up? And then here, this is almost like an open down parabola. This part right here, that's our inflection point. That part where it changes from what we say concave down to concave up. That is our cubic graph. Okay, and again, our inflection point is where it changes. Okay, guys, we still have about 3 more minutes. Right? We get 17. Okay, so the last one I want us to write down, okay, we'll start it so we have the spot, is our cube roots. Cube roots, which is y equal the cube root of x. And this one also has an inflection point or a locator point at 0, 0. And our general equation is going to be y equal, just like our square root graph, a times the cube root of x minus h plus k. And our inflection point is what makes that cube root 0, which is going to be positive h, and then the plus k. And a graph of this. I need to go in the center. I actually would adjust mine over a little more. You guys have more space than I gave myself. Now, when we're doing that, I'm going to think of it just like I did with the square root. What is the cube root of 0? 0. What's the cube root of 1? 1. What's the next nice cube root? 8. 8. Cube root of 8, because 2 cubed is 8. So I go to 8. 1, 2, 3, 4, 5, 6, 7, 8. And I'd be up at 2. I'm going to have the same on the negative side. So I'm going to go -1, -1. And I'm going to go -8. 1, 2, 3, 4, 5, 6, 7, 8. -2. Okay, I know we kind of rushed through this, especially this last one. But notice it kind of looks like a sideways cubic graph. Okay, so we will continue adding more notes into our composition book. We will do moved ones